Today's lesson is on polynomial functions, and this can get pretty involved, especially for those of you that have never seen anything like this before. So we're going to be looking at polynomial functions. We're going to graph them. We're going to talk about their ending behavior. We're going to use zeros to graph polynomials. We're going to talk about the shape of the graph near a zero, which means we might have what we call multiple zeros. And finally, we're going to look at local maxima and minima of polynomials. So let's first of all discuss a polynomial function and what it really is. So every polynomial can be written in what we call every term is what we call a power function. And we always start with the highest degree, highest power of the variable, and move down. The numbers in front are called coefficients. The number at the end, if there's no variable, is called a constant. Now, the leading coefficient is the first term's coefficient. So whatever the highest power is, the leading term or the leading coefficient is the first term. So let me give you an example quick of what a polynomial might look like. So let's go 2x to the 7th minus 4/5 x cubed plus x squared minus x plus 1. Let's say f of x is that function. Now you're looking at this going, whoa. Well, this is called a 7th degree polynomial. The leading term is 2x to the 7th, and our leading coefficient would be 2. And the highest power is a 7th, so we call that a 7th degree. Remember, we cannot change these from being positive real numbers. No, that's not even the word, integers. They have to be positive integers for the powers, or it's not a polynomial, and that is very important. Now, some things we need to talk about with polynomials. Any odd degree is what we call a chair function. And the reason it is because it looks like kind of a chair, like a lounge chair, like you could sit in this. So that would mean cube. Now, that doesn't count for 1. 1 is an odd number, but we don't include that as a chair function. So a 0, like x to the 0, is a horizontal line, okay? That's just a horizontal line. X to the first is also linear. So those are special polynomials. We don't really talk about those much. But x cubed, x to the 5th, x to the 7th, etc., we call chair functions. They're odd. Now the chair function, and we can put these on your calculator like y equal x cubed, y equal x to the 5th, y equal x to the 7th, negative 2x cubed. They're either going to rise from left to right or fall from left to right. So in other words, this first one here, the leading coefficient is positive, which means it moves up, it increases from left to right. If it's negative, it decreases from left to right. Okay, now let's talk about the end behavior. The end behavior is what is going on at the end. So the first part here, we're going to look down here. As y approaches negative infinity, let me rephrase that because this is a different book, so this is a different way of saying it. Y is going to negative infinity as x approaches negative infinity. So as we go down the x-axis here to our left, y is going down forever as well. As well as we go to positive infinity on the x-axis, y is also approaching infinity. That is called ending behavior. So in other words, y approaches negative infinity as x approaches negative infinity, and y approaches positive infinity as x approaches positive infinity. Conversely, if you look at a chair function that has a leading coefficient that's negative, like negative 2x cubed, could be this one, as y approaches positive infinity as x approaches negative infinity, and y approaches negative infinity as x approaches positive infinity. So that arrow, the word is approaches. So those are chair functions. All of them with odd powers are going to look something like that. Now they could look like this, okay? And then it has 3 zeros, you see that? So that's an x cubed, more than likely. It could look like this. Okay, 1, 2, 3, 4, 5. So this could be an x to the 5th. Okay. It could look like this. And who knows what that is? It could be a cube, but it's negative. The leading coefficient's negative. So all of those are what we call chair functions. Now, when the polynomial has an even degree that's the leading term, then we get a U-shape. So that's x squared, and I know that's a parabola, but in this case we're just going to call it U-shaped. So any even power now, and this is interesting, is going to look kind of like a U from the end behavior, meaning we're only concentrating on what's happening going to positive and negative infinity with the graph. In other words, we're not zoomed in on here. When we zoom in on there, that's called short run behavior. So you can see this one, who knows what it is? It's not a quadratic. It might be an x to the 4th. It might be an x to the 6th. Who knows? It might be x to the 8th. But here's what's important. It doesn't matter y is approaching infinity no matter what we approach on the x-axis when the leading coefficient is positive, because remember, it opens up like a parabola. When the leading coefficient is negative, it opens down. Therefore, y approaches negative infinity as x approaches positive and negative infinity. So that's pretty important stuff there. But even powers are U-shaped, odd powers are chair-shaped, chair functions. Now, here's an example. Determine the end behavior of the polynomial. The first thing, and I know we can look at the graph and we can see what's going on, that's no problem. But here's the important thing. Just look at the equation. It tells you everything you need to know. First of all, it's a quartic. It's a 4. So we know that it is U-shaped because it's an even power. The negative 2 says it's going to go down. Apologize. So as x approaches infinity then, or negative infinity, it doesn't matter, then y is going to approach negative infinity. So y approaches infinity? No, that's not right. Ooh, this is wrong. This should have a negative in front of it, shouldn't it? Y approaches negative infinity as x approaches infinity, and y approaches negative infinity as x approaches negative infinity. Now, when you write this out, you literally can write out y approaches negative infinity as x approaches positive and negative infinity and write it as one statement. Now, I don't think WebAssign will let you do that, but I will on a test or quiz. And there's the picture of it. And it makes perfect sense. As you go to the left, it goes down. As you go to the right, it goes down. So it's a U shape that is down. That's the end behavior of a polynomial. Now let's look at this guy. Again, we don't even need to graph it. We only look at the leading term. It's a 5. We know it's a chair. Now is that chair going Is it increasing or decreasing? Well, it's positive 3, so we know it's going to look something like that. So y approaches infinity as x approaches infinity, and as x approaches negative infinity, y approaches negative infinity. That is what we call the end behavior of the polynomial. Now, let's talk about the real zeros of a polynomial, meaning the short-run behavior. What's going on around the x-axis? Well, if p is a polynomial function and c is a real number, the following statements are equivalent. C is a zero of p. X equals c is a solution of the equation p of x equals 0. X minus a is a factor of p of x, and c is an x-intercept of the graph of p. Again, this is nothing new. I think we used the word root last year. We talked about this in class as well. It's a zero solution factor or root or x-intercept of the graph. Those are the zeros of a polynomial, an x-intercept. Now, what's happening to the shape of the graph near a 0? If c is a 0 of p of multiplicity m, then the shape of the graph of p near c is as follows. If m is odd, the graph crosses the x-axis at x equals c. If m is even, the graph touches the x-axis at x equals c. So let me interpret this a little better for you. Multiplicity m means we're going to have something like, let's say c is, we'll just say x minus c squared. Okay, we have multiple zeros of the same 0, because if I set this equal to 0, x minus c equals 0, x minus c equals 0, we get x equals c, x equals c. So it's the same number twice. Ladies and gentlemen, when you have an even power, you're going to have multiple zeros, 2, 4, 6, etc., and the graph will hug the intercept. I call it hug. Okay, that's my interpretation, not a book's. But when it's x minus c cubed, we're going to have multiple zeros. Oh, geez, I just said that wrong. This is backwards. Sorry. Of 3 or 5, sorry, you're going to get x equals c 3 times. That's a hug. But when you have a even power, sorry, x minus c to the second, x minus c to the fourth, that means it's going to bounce off. So odd power, it hugs the 0. And if it's an even power, it bounces off the x-axis. I shouldn't say hugs the 0, it hugs the axis, I think is a better way of saying it. Now that I've totally lost you, let me show you quick. Let's say we have this, okay, this graph. Well, I got a 0 here and I got a 0 here. Well, it's only 2 zeros, right? But I know it's a chair function. So I know it at least has to be x cubed. It at least has to be x cubed. It could be x to the 5th. But what I have here is a multiple 0. You know how I know? Because it bounces there. And when it bounces off, it's going to be an even power. Okay? And we'll get into it. We'll get an equation here in a second. It'll make a lot of sense. Okay, so find the zeros for the polynomial function f of x equal negative 2x to the 4th minus x cubed plus 3x squared. So we need to factor it, it says. Okay, and we'll set it equal to 0. I'm going to take out a negative x squared first. That leaves me with 2x squared plus x plus 3. No, minus 3, sorry. Now, the reason I took out a negative x squared is because it's easier to factor for me. Now, you can split the middle term and all that business, but I'm not going to because I know it's 2x times x, and I know it's got to be 3 and 1 somewhere. And now I'm going to check my outers and inners, and you could split the middle term if you want. It's up to you. I think it's going to be -1 and a +3. So now we check our inners. Our outers is -2x. Our inner is 3x. 3x minus 2x is positive x, positive 1x. So now we set each of these factors equal to 0. Okay? Yes, this is a factor. That's a factor, and that's a factor. Now, if you're good at algebra, you don't have to write all this out. You can just go right to that, and then you're stuck on this one. Well, I can divide by -1, so x squared equals 0, and then I take the square root of 0, which is 0. However, it's a squared. Therefore, it's 0 twice. We have what we call a multiple 0. And in this case, the multiple 0 is 0. So what am I talking about here? Okay, so if I just graph these points, stay with me here, and I say there's x equal 1, there's -1, there's -2, -3 halves in between, and we got a multiple 0 at 0. Now remember, when you have a squared, it bounces. And this goes down. Now, I have no idea what it looks like, but I know it's going to be a U because it has a 4, and I know it's going to open downward. So it's going to look something like this. How do I know that? Well, I know one of my zeros is -3 halves. I know one of my zeros is 1. But I also know that I have a multiple 0 at 0. So instead of going through 0, it's going to bounce off because we have a squared. That is what the graph, if you put it in your calculator, that is close to what it's going to look like. And that's without me using a calculator. So you can kind of see what the end behavior and the short run behavior of this function is doing. Okay, find the zeros for this one. We're going to do the same thing. We're going to factor it, and we'll see how easy that is. Looks like a cubed. I don't think we probably remember. I don't remember how to factor these, but I'm going to check and see if this can be factored by grouping. Remember doing that? You take out an x squared, we're left with x minus 4. You take out a -25, you're left with x minus 4, right? Yep. So you have x squared minus 25 and x minus 4, but that factors again. There we go. So all those factors equal 0. So we have x equal -5, x equal 5, and x equal 4. And it's a cubic, so it's perfect. We know it's a chair. We know that the leading term is, leading coefficient is a 1, so it goes up. So if this is -5 and that's +5, 4 is going to be like right there. We're going to have a 0 at -5, 4, and 5. And this goes up from left to right, so it's going to look something like this. I know it's goofy, but we zoomed in, okay? So something like that. And since that says 100, it might even go up way up here and then come down. I'm guessing that's what it does if you put it on your calculator. But it should give us an idea. We know it's a chair because of the cube. We know this one's a U because of the 4. Okay, now we're going to write formulas of polynomials from a graph, okay? And I encourage you to pause this and read those. I'm not going to read those to you. I'm going to do the examples. So here we go. The first thing is we look at the zeros. There are 3 of them. The second thing we should notice is that it's a U. So we know it's either a x squared, x to the 4th, x to the 6th, etc. We don't really know. And there's no way of being certain. What we do know, though, is it can't be this one. because we know x squared is a parabola. So it could be x to the 4th, x to the 6th, x to the 8th, etc. But wait a minute, Mr. Thamer, wait a minute, whoa. There's only 3 zeros. There should be 4 if it's an x to the 4th. There should be 6 if there's, well, in this case, though, we have multiplicity at 2, right? So this function then, now I'm going to put an A because we have to have whether it opens up or down, and we don't know what that A is, so we'll just leave it like that. And then write all the factors we see. Well, we have x, okay, x equal negative 2, right? But to get that, you have to have x plus 2. Oh, not 2, sorry. That's a 3. X equal negative 3, so we have to have x plus 3. X equal 2, so we have to have x minus 2. X equal 5, so we have to have x minus 5. Now here's the problem. We have multiplicity at 2. So that means it bounces off. So that is an even power. So it could be a 2, it could be a 4, it could be a 6. Always pick the easiest one, which is the lowest one. And we're done, right? We got the equation? Well, actually we don't, because we don't know what A is. However, we can find it by using a different point. In this case, it looks like we could use the point 0, negative 2. So we plug it in. Negative 2 equals A, 0 plus 3, 0 minus 2 squared, times 0 minus 5. And then we solve for A. So we get 3 times negative 2 squared times negative 5. I believe that's going to be 4, 12, that's be negative 60, correct? Divide by negative 60, I got 1/30. So then f of x is going to equal 1/30 x plus 3, x minus 2 quantity squared, x minus 5. Now it can be in any order. But that equation, if you graph it on your calculator, will give you that graph right there. Pretty cool, isn't it? Okay, let's see if we can get another. Oh, I see another multiplicity. Zoom in a little bit here. So we have x equal negative 2, but it's multiple. We have x equal 1, and we have x equal 2. And this looks again like a U, this U shape. So that's got to be well, it can't be a squared, can it? But it might be a 4th or a 6th. It doesn't matter. We know we have multiples here. So that's going to be f of x equals a, let's see, x plus 2, right? That's how you get negative 2 for your 0. So the factor is x plus 2, the opposite. And it bounces, so we're going to use a squared. X minus 1, x minus 2. Excuse me. Now can we find another point? I think we have one here. Now we're kind of guessing, but it looks like 0, negative 4 is a point we can use. We shall find out if it's going to look nice. So we put 0 in for x and negative 4 for y, and then solve. That's 2 squared, which is 4, times negative 1 times negative 2. That's 8, isn't it? So a is negative 1/2. So f of x equals negative 1/2, x plus 2 quantity squared, x minus 1, x minus 2. If you want to check your calculator, it will look like that. Pretty cool. And we're done. WebAssign, 3